Imagine a factory conveyor belt loaded with thousands of open bottles, each one filled to the very brim with a bright blue liquid. To move these without a disaster, you need an incredibly steady hand. But standard industrial motors have a massive limitation. They don't have a way to ease into motion. They really only have two settings, completely off or instantly running at 100% power. When an operator presses the start button, the motor doesn't wake up slowly. It immediately demands every bit of energy the building can provide. Because of that instant surge of power, the entire machine violently jerks forward. That single second of force is enough to splash liquid everywhere, ruining the product before it even leaves the starting line. Beyond the wasted product, there's a hidden mechanical cost. That sudden snap from a standstill to full speed stretches the heavy rubber belts and can even cause them to smoke and burn from the friction. This instant force also hammers the metal gears inside the machine and puts a massive amount of stress on the motor's own internal components. Using electricity this way is like trying to drive in a parking lot by stomping the gas pedal to the floor. It's a crude, destructive way to handle a task that actually requires a delicate touch. To fix this, we use a device called a variable frequency drive, or VFD. Think of it as a smart translator that sits between the wall outlet and the motor to act as a precision controller. It's no longer shuffling back and forth, appearing on a graph as a series of bouncing bumps. Next, it passes through a smoothing stage, filling the gaps until the power is perfectly calm and flat. We are now left with a steady, predictable pool of energy called direct current. You can't build a precision machine on a shaky foundation. By turning that chaotic wall power into a smooth, flat pool of energy, the VFD now has the perfect starting point to control the motor. But there's a catch. The motor still needs that alternating back and forth flow to actually spin. Our goal now is to turn that flat pool of energy back into a flow we can control. To do this, the VFD uses a set of incredibly fast electronic switches that flick on and off thousands of times every second. Instead of one big wave, switches chop the power into tiny square pulses. To speed up the motor, those switches hold open longer. These wider pulses deliver more energy and electrical pressure. To slow down, narrower pulses are used, delivering less energy to ease back. Now, you might think that chopping the power into these harsh square bits would make the motor shake or vibrate like a flickering light. But the motor has a natural way of handling this. Inside are heavy coils of wire that have a lot of electrical momentum. They naturally resist sudden changes. These coils act like a heavy flywheel, soaking up those sharp square pulses and smoothing them out, turning digital chops into perfectly fluid circular motion. By changing switch times, the VFD provides total speed control, and because it balances the timing of these pulses with the electrical pressure, the motor keeps all its muscle, even when it's barely crawling. Let's look at that same conveyor belt again, but this time it's being managed by the VFD. We've programmed the device with a ramp. This is a set of instructions that tells the motor to gradually climb from a standstill to full speed over several seconds. When the operator hits start, there is no violent surge. The VFD sends exactly the right amount of energy to get the belt moving, increment by increment. The belt glides to life. It accelerates seamlessly to its cruising speed, and the liquid in those bottles doesn't move a single millimeter. Because the VFD manages the muscle and speed so carefully, the motor never has to strain or overheat. The belts don't stretch, and the gears don't grind. These devices are the hidden reason why modern factories can be so fast and so precise at the same time. They take raw, destructive electrical power and turn it into graceful, controlled motion.